Hey everyone! In this video, we're going to learn about two-dimensional projectile motion. We'll start with an overview of 2D projectile motion and look at the equations that we're going to use. We'll spend some time exploring two different examples: an object launched horizontally from an initial height and an object launched from the ground at an angle. In each example, we'll use the equations to find the x and y positions and see how they change over time. Then we'll do the same thing for the x and y velocities. We'll also talk about the motion graphs for each example. Then we'll learn more about the range of projectile motion and how it relates to the launch angle. Finally, we'll check out the motion graphs for some other examples. At the end, we'll do a summary of the main points. Let's start with an overview of two-dimensional projectile motion. We covered the basics of projectile motion in the introduction video, so watch that one first. In the last video, we learned about one-dimensional projectile motion, where an object only moves up and down. 2D projectile motion just adds a horizontal velocity, and it's very similar to 1D projectile motion. So watch that video if you haven't already. In 1D projectile motion, we only dealt with motion in the y direction. In 2D projectile motion, we have motion in the x and y directions. Whenever an object moves sideways through the air, it's in 2D projectile motion. This shows up everywhere, especially in sports. The initial velocity and angle determine how far the ball travels and how high it is at each point. They also determine the direction of the velocity at every point along the path. Changing the initial angle just a few degrees changes the entire trajectory. Even if something moves really fast, gravity still causes it to fall down, so its path is never a straight line. We usually focus on the path of one object, but 2D projectile motion can help us understand other things, like the shape and range of a stream of water. If we ignore air resistance, an object always falls at the same rate due to gravity, 9.8 meters per second squared. So a ball that's launched horizontally will hit the ground at the same time as a ball that falls straight down. So what's different about 2D projectile motion that we haven't already covered? In 1D projectile motion, an object moves in the y direction and it doesn't move sideways. The initial velocity is also the initial y velocity. The velocity in the x direction is 0. But in 2D projectile motion, an object does move sideways, so it has some velocity in the x direction. The initial velocity is not vertical, it's usually at an angle. So now we have an initial y velocity and an initial x velocity. The acceleration in the y direction is always 9.8 meters per second squared downwards. But there's no acceleration in the x direction. Ax is 0. So the horizontal velocity, Vx, is constant the entire time. The final x velocity at any time is the same as the initial x velocity. In 2D projectile motion, we call the horizontal displacement the range of the projectile motion. That's how far the object travels in the x direction. For 2D projectile motion, we're going to use the same kinematic equations for the y direction, but we also need some equations in the x direction. Since there's no horizontal acceleration, we won't use the x equations with acceleration, so we just have the displacement and velocity equations. And remember, the equations can be rearranged in different ways. If we say up is the positive y direction, then we're going to plug in negative g, negative 9.8 meters per second squared, for ay. Finally, even though the variables in the x and y equations are different, time shows up in both directions. t has the same value in both equations at the same moment in time. So we can use time to connect the x and y equations. In 1D projectile motion, there's only 3 initial conditions. In 2D projectile motion, we have some new scenarios. Let's say up is the positive y direction and right is the positive x direction. If the initial angle is above the horizontal, the initial y velocity points upwards, so it's positive. The final height could be the same as the initial height, like if it starts and ends at the ground. The final height could be greater than the initial height, like if it's going over a wall or landing at a higher point. Or the final height could be less than the initial height, like if it's launched from a cliff. If that's the case, the initial velocity could also be horizontal, so the initial y velocity is 0. Or the angle could even be below the horizontal, so the initial y velocity points downwards and it's negative. The only difference between these scenarios is the initial and final values, and the positive and negative signs. But the motion behaves the same way in each case. We're going to use the same equations and solve problems the same way for each one. So that's an overview of 2D projectile motion. Now let's explore some examples. Example 1 is an object with an initial horizontal velocity. A ball starts at a height of 19.6 meters with a horizontal velocity of 10 meters per second. For 2D projectile motion, here's some questions we might see. How far does the ball travel? How long is the ball in the air? And what is the speed of the ball when it lands? These questions are just asking for a value at a specific point in the motion, like when the object hits the ground. But let's start by exploring this motion and come back to these questions later. With projectile motion, it's not really important why the object has its initial height and velocity. In this example, the ball is shot out of a cannon on a cliff. But we really just care about the projectile motion of the ball, so all we need is the initial height and the initial velocity. Now that this is two-dimensional motion, we need to choose the origin where x and y are 0, and which directions are positive. You can set this up differently, but let's place the origin at the ground, directly below the initial position, and we'll say right is the positive x direction and up is the positive y direction. Using this coordinate system, the ball's initial x position is 0 meters, and the initial y position is 19.6 meters. We could also write the initial position using coordinates. As a side note, we're usually describing the projectile motion of an object's center of mass. When we draw a picture, the object is going to have some width and height, so keep in mind that we're describing the center of the ball, so it hits the ground when its center has a y position of 0. The initial velocity is 10 meters per second, and it's in the horizontal direction. That means the initial x velocity is 10 meters per second. The initial y velocity is 0 because this vector has no y component. It only points in the x direction. Since this is projectile motion, the acceleration due to gravity, g, is 9.8 meters per second squared downwards. Since we chose up to be the positive y direction, then ay, the vertical acceleration, would be negative g, negative 9.8 meters per second squared. So that's our setup. Now let's see what this motion looks like. The ball moves to the right and falls down at the same time. What's happening to the x position over time? What about the y position? And what do you think is happening to the velocity in the horizontal and vertical directions? Are they increasing, decreasing, or staying the same? Here's some grid lines and snapshots of the ball's position at half-second intervals. How much does the ball move to the right during each interval? And how much does it move down? If we draw lines from the ball to the y-axis, we can see how the y position is changing over time. The spacing between each line gets longer. As the ball moves, it falls a greater distance in the vertical direction during each second, or each half second. Now let's look at the motion in the x direction. The spacing between each snapshot is the same. The ball moves the same horizontal distance during each interval. So why are the vertical and horizontal motions different? 2D projectile motion is one example of an important concept in physics that we mentioned in a previous lesson. An object's x motion and y motion are independent of each other. The vertical motion does not affect the horizontal motion, and the horizontal motion doesn't affect the vertical motion. We know that objects in projectile motion experience a downwards acceleration due to gravity. Since gravity only acts in the vertical direction, gravity only affects the vertical motion. So if we look at the y position over time, the ball is accelerating downwards due to gravity. That acceleration causes the vertical velocity to increase. The ball speeds up in the vertical direction and falls a greater distance during each second. This should look familiar because it's the same as one-dimensional projectile motion, sometimes called free fall. This is a really important concept. The vertical motion of the ball shot out of the cannon is identical to a ball falling straight down. The initial velocity is horizontal, so the initial vertical velocity is 0. That's the same thing as being dropped from rest, if we're only looking at the y motion. The balls have the same height and velocity at each time point, and they hit the ground at the same time. The fact that the ball is also moving to the right has no effect on its vertical motion. So why is the horizontal motion different? Well, there's no gravity in the x direction, so there's no acceleration in the x direction. Gravity pulls the ball down, but it doesn't pull it to the right or left. If the x acceleration is 0, then the x velocity is constant. It doesn't change over time. So the ball moves the same distance in the x direction during each second. We could think of the ball's horizontal motion as being identical to a ball rolling on the ground at a constant velocity. Or if we turned gravity off, the ball would move in a straight line at a constant speed. The difference between this path and the ball's actual path is the amount the ball falls due to gravity. But the vertical acceleration has no effect on its motion in the x direction. As an analogy, here's a bird's eye view of a curling stone sliding on ice with no friction, which we used in some previous videos. This is 2D motion on a horizontal plane, so the x and y directions are both horizontal on the ground. If we give this stone a push in the x direction, so we give it an initial x velocity, it'll move in a straight line at a constant speed if there's no friction. Now imagine we attached a model rocket engine to the curling stone. When we light the engine, it causes the curling stone to accelerate. If we point it in the negative y direction, the y velocity will increase and the stone will move further during each interval of time. Now, what if we light the engine and, at the same time, we give the stone a push in the x direction? Now the stone follows this curved path, which is a combination of a constant velocity in the x direction and acceleration in the y direction. In this example, the acceleration is caused by the rocket engine. In projectile motion, the acceleration is caused by gravity. This picture will change a little bit when we have different initial values, but this is how two-dimensional projectile motion works. The ball has separate x and y positions, separate x and y velocities, and we use separate x and y equations. But we can take the x and y velocities and combine them to get the actual velocity vector of the ball at any time. We can draw the components like this, or we can draw them so they form a right triangle with the vector. V is the instantaneous velocity vector of the ball. It shows the ball's actual velocity through the air and the direction of its motion at each instant. This might be the first time we're seeing a velocity vector on a curved path, where the direction is changing. Notice that the velocity vector does not trace the path of the object. The path is curved, but a vector is just a straight arrow. The velocity vector is always tangent to the path, and it shows the direction of the velocity at one instant. So now that we have an idea of how things work, let's use the equations and see what the motion graphs look like for this example. Here's the information we have. First, let's use this equation to find the y position at each time point. Like we mentioned in the last video, the first variable in this equation is written as y final. When we solve for the y position at each time, you can think of each one as the final y position in the equation, but we're just going to write them as y with no subscript. At the point where t equals 0.5 seconds, we can plug in 19.6 meters for the initial y position, 0 meters per second for the initial y velocity, 0.5 seconds for the time, and negative 9.8 meters per second squared for the y acceleration. That gives us 18.4 meters for the y position at 0.5 seconds. We can do the same thing for each time point by plugging in the same initial values and the different times. At 1 second, the y position is 14.7 meters. At 1.5 seconds, it's 8.6 meters. And at 2 seconds, the y position happens to be 0 meters. So we can see the y position, the height, is decreasing as the ball falls. Here's the y displacement between each point. The ball is moving further during each interval because it's accelerating. Here's the graph of the ball's y position versus time and the points we just found. The horizontal axis is time in seconds, and the vertical axis is the y position in meters. The line starts at the initial y position, 19.6 meters. It decreases over time, and it crosses the horizontal axis at 2 seconds. That's when the y position is 0 and the ball hits the ground. The graph is a curved line because the ball is accelerating in the y direction. The graph and the actual path of the ball are parabolas, but this graph is not showing us the two-dimensional path of the ball. It's just showing us the y position over time. If the ball was falling straight down, this graph would be the same. It's just showing how the y position is changing. Also, this is a graph of this function, which is the kinematic equation we used with the initial values, and it's written as the y position as a function of time. Now let's find the y velocity at each time using this equation. This tells us how the velocity is changing over time due to an acceleration. When t equals 0.5 seconds, we can plug in 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, and 0.5 seconds for time. That gives us negative 4.9 meters per second for the y velocity at that time. At 1 second, the y velocity is negative 9.8 meters per second. At 1.5 seconds, it's negative 14.7, and at 2 seconds, it's negative 19.6. Here's what the y velocity vectors look like as the ball falls. They're always negative because they point in the negative direction, but the magnitude is increasing. The ball is speeding up. If we look at the y velocity at 1 second intervals, it's changing by the same amount each second. That amount is the acceleration, negative 9.8 meters per second. And here's the graph of the y velocity versus time. The horizontal axis is time, but now the vertical axis is the y velocity in meters per second. Up is the positive direction, and down is negative. It starts at 0 meters per second, which is the initial y velocity. The slope of the velocity graph is the acceleration, the change in velocity over the change in time, which is negative 9.8 meters per second per second. Here's the y position, y velocity, and y acceleration graphs together. The y acceleration is always a constant negative 9.8 meters per second squared, so it's a flat line. The slope of the velocity graph is the acceleration. The acceleration is negative, so the slope of the velocity graph is negative. And the slope is constant, so the velocity is a straight line. The slope of the position graph is the velocity, the change in position over the change in time. At 0 seconds, the slope of the position graph is 0, and the velocity is 0. At 1 second, the slope of the position graph is negative 9.8, which is the velocity at 1 second. The velocity is changing, so the slope of the position graph is changing, which makes it a curve. Now let's look at the motion in the x direction. There's no horizontal acceleration, so we can use this equation to find the x position at each time. At t equals 0.5 seconds, we plug in 0 meters for the initial x position, 10 meters per second for the x velocity, which is always the same as the initial x velocity, and we plug in 0.5 seconds for time. That gives us 5 meters for the x position. At 1 second, the x position is 10 meters. At 1.5 seconds, it's 15 meters, and at 2 seconds, it's 20 meters. Notice how the x displacement is the same for each interval because the x velocity is constant. The ball moves 5 meters to the right every half second. Here's the graph of the x position versus time. Now, the vertical axis of the graph represents the x direction. The initial position is 0 meters, and as the ball moves to the right, the line on the graph moves up. This is how motion graphs are set up. We always have time on the horizontal axis. This is a graph of this function, which is the kinematic equation we just used. The y-intercept is 0, which is the initial x position, and the slope is 10, which is the x velocity. Notice how there's nothing special about this graph at 2 seconds when the ball hits the ground. The line doesn't stop, cross an axis, or reach some maximum value. If the ground wasn't there to stop the motion, or if there was no gravity, the graph would be the same and the ball would keep moving to the right forever. So if we want to find the x position when the ball hits the ground, which is the range of the projectile motion, we first need to find the time it hits the ground using the y motion. In this case, that's at 2 seconds. Then we can find the x position at that time, which is the range. What about the velocity in the x direction? Well, since there's no acceleration in the x direction, the x velocity is always the same as the initial x velocity, 10 meters per second. The magnitude, or length, of the x velocity vector doesn't change over time. Here's a graph of the x velocity versus time. It's not that interesting, but it is another way to show that the x velocity is a constant 10 meters per second. And here's the graphs for the x position, x velocity, and x acceleration. These are just the graphs for an object with a constant velocity, so again, they're not as interesting as the y graphs. The acceleration in the x direction is 0, the velocity is always positive 10 meters per second, and the x position increases over time. Since the acceleration is 0, the slope of the velocity graph is 0. And the velocity is constant, so the slope of the position graph is constant, and it's a straight line. So that's what two-dimensional projectile motion looks like when an object starts at some height with a horizontal velocity. Now that we've looked at the motion, let's answer a few questions. How long is the ball in the air? How far does the ball travel? And what is the speed of the ball when it lands? Let's start with the first one. We mentioned earlier that the time in the air is only determined by the y motion. So we're looking for the time when the ball hits the ground, which is the time when the y position is 0. The only equation we can use with the information we have is this one. We can plug in 0 meters for the final y position when the ball hits the ground, 19.6 meters for the initial y position, 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the acceleration, and we want to solve for t. We can simplify this equation, add 4.9 t squared to both sides, divide by 4.9, take the square root of both sides, and we get 2 seconds for t. That's the time when the ball reaches 0 meters, and it's how long the ball is in the air. Next, how far does the ball travel? This is asking for the displacement of the ball in the x direction, which is the range of the projectile motion. How do we find that? We know the ball is moving to the right at a constant velocity, and now we know how long the ball is in the air, 2 seconds. That time applies to the y motion and the x motion. That's how long the ball has to move to the right, so we can use that time and the velocity to find the displacement. So let's use the equation for the x velocity. We can multiply both sides by time, and then plug in 10 meters per second for the x velocity and 2 seconds for the time. This equation uses delta t, but that's the same as t because the initial time is 0. When we multiply those together, we get 20 meters for the x displacement, which is the range. We'll talk more about range later in the video. Finally, what is the speed of the ball when it lands? Are we looking for the x velocity or the y velocity? When a question asks for the speed or velocity of an object in 2D motion, it's talking about the actual velocity vector, which is the combination or the vector sum of the x and y velocity components. So the final velocity vector is the combination of the final x velocity and the final y velocity. Speed is the magnitude of velocity, which is the length of the velocity vector. So if we know the components, we can find the magnitude using the Pythagorean theorem. We already know the final x velocity. It's the same as the initial x velocity, 10 meters per second. So we need to find the final y velocity. We could use this equation and plug in the time when the ball hits the ground. Or we could use this equation and plug in the final y position. The first equation only works because we already found the time, so let's use this equation. We plug in 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, 0 meters for the final y position, and 19.6 meters for the initial y position. If we simplify that and take the square root of both sides, we get 19.6 meters per second. Notice that this equation only deals with positive values for the velocities because they're squared in the equation. So it's really giving us the final y speed, or the absolute value of the final y velocity. The y velocity points in the negative direction, so the final y velocity would be negative 19.6 meters per second. So now we know the x and y velocity components when the ball hits the ground. Remember from the lesson on vectors that we use the Pythagorean theorem to find the magnitude of a vector, which is the hypotenuse. So the final velocity is the square root of the final x velocity squared plus the final y velocity squared. We plug in 10 meters per second and negative 19.6 meters per second, and we get 22 meters per second for the magnitude of the final velocity, which is the final speed. Alright, so that's an example of two-dimensional projectile motion where an object starts at some height with a horizontal velocity. Now let's look at one more example where an object has an initial velocity at an angle. We'll go through this one faster. A ball is launched from the ground with a velocity of 22 meters per second at an angle of 63 degrees. If the angle isn't described relative to the vertical or some other line, we'll assume it's 63 degrees above the horizontal, or above the ground. For this example, we'll place the origin right at the starting point of the ball, so the initial x and y positions are both 0. How is the ball being launched from the ground? Like we said before, that doesn't really matter for projectile motion. We just care about the initial height and the initial velocity. We could say the ball was kicked into the air, or maybe it was shot out of a cannon below ground level. The point of a setup like this is that the initial and final heights are both 0. Next, what do we do with this velocity vector? In pretty much every case, we need to find the components, the initial x velocity and the initial y velocity. Remember, a vector and its components form a right triangle, so we can use the right triangle trig relationships. The initial x velocity is the initial velocity times the cosine of this angle, which is 10 meters per second. The initial y velocity is the initial velocity times the sine of this angle, which is 19.6 meters per second. Cosine and sine don't always go with x and y. Just remember that cosine is for the component adjacent to the angle we're using, and sine is the component opposite from the angle. So these are the initial x and y velocities. When the ball is launched, its actual velocity is 22 meters per second in this direction, but it's moving up at 19.6 meters per second, and it's moving to the right at 10 meters per second at this initial time. Now we have all the initial values. So what does this motion look like? What's happening to the x and y positions over time? What about the x and y velocities? Is there anything about this that's similar to the last example? Here's the ball's position at half-second intervals. The ball moves up, reaches a maximum height, and then falls down. And it's moving to the right the whole time. If we look at the horizontal motion, the ball moves the same distance to the right during each interval. Just like before, the x velocity is constant because there's no acceleration in this direction. The ball is moving 10 meters per second to the right the whole time, so the ball moves the same amount each second. It's the same motion as a ball rolling on the ground at 10 meters per second. It doesn't matter what's happening in the vertical direction, the horizontal motion will always be the same. Now let's look at the vertical motion during the period when the ball is moving up. The distance between each height is getting shorter over time. Why is that? Gravity is acting downwards, in the opposite direction as the velocity. If the velocity is positive and the acceleration is negative, the velocity will decrease over time, and the ball slows down in the vertical direction. So the ball moves less vertical distance during each interval. Then the ball reaches a maximum height and falls back down. As the ball falls, the y velocity increases, and the ball falls a greater distance during each interval, just like we saw in the first example. So for the first half, the ball moves up, but it slows down in the y direction. During the second half, the ball falls down and moves faster in the y direction. Notice that the height of the ball is the same at equal times before and after the maximum height. Half a second before and after, it's at this height. 1 second before and after, it's at this height. Since the initial and final heights are the same, this trajectory is symmetric. The ball takes 2 seconds to move up and 2 seconds to fall down. Also, notice that this is the same vertical motion as a ball that's launched upwards at 19.6 meters per second. Just like with 1D projectile motion, when the ball reaches the maximum height, the y velocity is 0 because it's reversing direction. The ball is still moving to the right, but it's not moving up or down at that moment. So the horizontal velocity is constant, but the y velocity changes because of the acceleration due to gravity. If we combine the x and y velocity components at each time point, we can see the actual velocity vector of the ball. The x components stay the same, but the y component changes, which changes the length and direction of the vector. The vector always points in the direction of the ball's motion, and when the ball is at the maximum height, the y velocity component is 0, so the velocity is just the x velocity. If we line up the vectors at each time, we get a different view of how the velocity vector is changing. The x velocity stays the same, but the y velocity starts pointing up, then gets shorter until it's 0. Then it flips and gets longer in the negative direction. So the vector changes length and it rotates. Now let's quickly run through the actual values of the positions and velocities. Then we can look at the motion graphs for this example. Let's start with the x motion. We can use this equation to find the x position at each time point like before. We plug in 0 meters for the initial x position, 10 meters per second for the x velocity, and the times to get the x positions. The x velocity is constant, so the ball moves 5 meters during each half-second interval. Here's the graph of the x position versus time. It starts at 0 meters and increases with a constant slope, which is the velocity. Since the x velocity is constant, it's always the same as the initial x velocity, 10 meters per second. If we graph that, it's just a flat line. Here's the position, velocity, and acceleration graphs for the x motion. The position goes from 0 meters to 40 meters, the velocity is always 10 meters per second, and the acceleration is 0. These are the same graphs that we'd have for a ball rolling on the ground at 10 meters per second, since we're only looking at the motion in the x direction. Now let's look at the y motion. We can use this equation to find the y position at each time. The initial y position is 0 meters, the initial y velocity is 19.6 meters per second, and the y acceleration is negative 9.8 meters per second squared. When we plug in each time, we get the y positions. Notice how the y position increases from 0 to 2 seconds, then it decreases. We don't need to calculate the up and down motions separately. This equation covers the entire vertical motion. The initial velocity is positive, and the acceleration is negative, and that's how the math works out. Here's the graph of the y position versus time. It starts and ends at 0 meters, and it reaches a maximum height of 19.6 meters at 2 seconds. This graph looks like the two-dimensional path of the ball, but it's not. It's just showing us the y position over time. This is the same graph as a ball that's launched directly upwards with the same initial y velocity. We can find the y velocity at each time using this equation. The initial y velocity is 19.6 meters per second, and the y acceleration is negative 9.8 meters per second squared. Notice how the velocity starts at positive 19.6, it decreases to 0 at 2 seconds, then it becomes negative and increases in magnitude. Again, this is how the equation works. The initial velocity is positive, and we subtract from it each second because the acceleration is negative. Here's the graph of the y velocity versus time. It starts at 19.6 meters per second and ends at negative 19.6 meters per second. It has a negative slope, which is the acceleration. And this is the same velocity graph as a ball launched directly upwards. The velocity starts out positive, it slows down to 0 at the maximum height at 2 seconds, then it becomes negative as the ball falls down. And the velocity has the same magnitude at equal heights, except the direction is flipped. Here's all the graphs for the y motion. The slope of the position graph is the velocity, so the position starts with a positive slope, the slope decreases to 0, then it increases in the negative direction. So how does this motion compare to the first example? In that example, the ball started at some height with a horizontal velocity. That motion is just the second half of this motion. It just starts 2 seconds later when the ball is at the maximum height. The x velocity is 10 meters per second and the y velocity is 0. They both take 2 seconds to fall from the maximum height to the ground. Here's the x and y positions and velocities for the second example. If we start the clock 2 seconds later, we get the values for the first example. If we start with the y motion graphs from the second example, and we shift them 2 seconds to the left, we get the graphs from the first example. So the ball starts at a height of 19.6 meters and a y velocity of 0. And the same is true for the x motion graphs. The x velocities are the same, but in the first example, the ball is in the air for half the time, so it only travels half as far before hitting the ground. Now let's wrap up this example by finding the speed of the ball when it lands. Just like the first example, the final velocity vector is the combination of the final x velocity and the final y velocity. We know the final x velocity, so let's find the final y velocity using this equation. We plug in 19.6 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, 0 meters for the initial y position, and 0 meters for the final y position when it hits the ground. Since the initial and final y positions are the same, the terms on the right are multiplied by 0. The final y velocity squared is equal to 19.6 squared, so the final y velocity is 19.6 meters per second. Again, this equation actually gives us the speed because v is squared. The final y velocity is negative 19.6 meters per second, since it points downwards. Now that we have the final x and y velocities, we can use the Pythagorean theorem to find the speed, which is the magnitude of the final velocity vector. When we do that, we get 22 meters per second for the final speed of the ball. This is the same as the initial speed when the ball is launched. That's because the initial and final heights are the same, and the trajectory is symmetric. So we could have just answered this question by remembering that concept. Finally, what if we wanted to answer this question? How far does the ball travel? Let's talk about one of the important concepts in projectile motion, which is range. Range is how far the object travels in the horizontal direction. It's the displacement in the x direction. So what determines the range? How do we find delta x? Here's the equation for the x velocity. If we know Vx and delta t, we can find delta x. Vx is the horizontal velocity, which is always the same as the initial horizontal velocity. Delta t is the amount of time the object is in the air, which only depends on the y motion. We actually did this in the first example, but let's outline the steps for finding the range. First, we need to find the initial x and y velocities, the components of the initial velocity vector. For this example, the initial x velocity is 10 meters per second, and the initial y velocity is 19.6 meters per second. Second, we need to find the time in the air using the y motion. If the initial and final heights are different, like if the object is launched off a cliff, we need to use this equation to find the time. But if the initial and final heights are the same, like in this example, the trajectory is symmetric, so we know the final y velocity. Then we can use this equation for acceleration. The change in the y velocity is the final y velocity minus the initial y velocity. We can rearrange the equation so time is on the left, then plug in the values for the velocities and the acceleration, and we get 4 seconds. That's the duration of the motion, the amount of time the ball is in the air. Third, we use that time to find the range, delta x. The x velocity is the initial x velocity, 10 meters per second, and the time is 4 seconds. That gives us 40 meters for the range. Here's all 3 steps. It's always good to understand how to solve a problem like this, but we could combine these steps and come up with an equation for the range using any velocity and angle. We'll move through this quickly, so feel free to pause at any point. Also, see if you can derive this equation on your own based on these steps. We'll use this equation to find the time in the air. We replace the initial y velocity with the initial velocity times the sine of theta, and replace the acceleration with negative g. Then we rearrange things so we can use the quadratic formula. We can keep y initial and y final, or we can say y final is 0. We plug these coefficients into the quadratic formula, simplify that, and we get an equation for t, the time in the air. The range is the x velocity times the period of time. We replace the x velocity with the initial velocity times the cosine of theta, and we replace t with the equation we just found. So this is the range equation for any projectile motion. But if the initial and final heights are both 0, then we can simplify this a lot more. Y initial is 0, so the square root term simplifies to vi times the sine of theta. Then we can use this trig identity, 2 times cosine times sine equals the sine of 2 theta. Then we end up with this. This is the range equation you might see more often. Keep in mind that this only applies if the initial and final heights are equal, like if the object starts and ends at the ground. One more question that shows up a lot is this. What launch angle results in the longest range? So what value of theta will give us the maximum value of delta x? Here's the graph of this equation using 22 meters per second for the initial velocity. The angle, theta, is on the horizontal axis from 0 to 90 degrees, and the vertical axis is the range, delta x. No matter what the initial velocity is, an object launched from the ground will travel the farthest when it's launched at 45 degrees. If the angle is lower, the x velocity is faster, but the object spends less time in the air. If the angle is higher, the object spends more time in the air, but the x velocity is slower. Another important thing to know is that the range is the same at equal angles above and below 45 degrees. So the ball travels the same distance if it's launched at 30 degrees or 60 degrees, which are both 15 degrees away from 45. and the ball travels the same distance at 15 degrees and 75 degrees. But what if the object is launched from an initial height? Then the initial and final heights are not the same, so we use the general range equation, and the graph looks different. It's no longer a regular sine curve. More importantly, if the initial height is greater, the maximum value shifts to the left. If we keep the initial velocity of 22 meters per second, but the object starts at a height of 20 meters, the angle that gives us the maximum range is 36.6 degrees, which is less than 45. So that's a closer look at range in projectile motion. We covered 2 examples in this video, but there's other scenarios for 2D projectile motion. The only difference is the initial and final heights and the angle of the initial velocity, but they all follow the same rules that we covered in this video, and we would solve problems the same way in each case. To wrap up 2D projectile motion, here's what the motion graphs would look like for each scenario. This is the second example that we did, where an object starts and ends at the ground. We'll say the origin is on the ground at the initial x position. The x motion graphs are the same for every scenario, so we'll just show them for this example. The acceleration is 0, the velocity is constant, and the x position increases linearly. And here's the y motion. The y position starts and ends at 0, and the y velocity goes from positive to negative. The object reaches the maximum height and 0 y velocity halfway through the motion. The y acceleration graph will be the same in every case, negative 9.8 meters per second squared, if up is positive. If the final height is greater than the initial height, the y motion looks like this. They're basically the same, but they stop earlier. The trajectory is not symmetric, so the time when it reaches the maximum height and 0 velocity is not in the middle, it's later. If the initial height is greater than the final height and the launch angle is upwards, the graphs look like the last example, but they're flipped. The y position starts at some height and ends at 0. It reaches the maximum height and 0 y velocity in less than half of the total time. If the launch angle is 0, so the initial velocity is horizontal, the y position starts at the maximum height with 0 slope, and then it decreases to 0. And the y velocity starts at 0 and increases in the negative direction. And finally, if the launch angle is below the horizontal, the y velocity starts out negative and increases in the negative direction. The y position starts with a negative slope and goes to 0. Alright, so that's everything we're going to cover in this video. Let's do a summary of 2-dimensional projectile motion. In 1D projectile motion, an object only moves up and down in the y direction. In 2D projectile motion, an object moves in the x and y directions. We use the same y equations, but we don't use x equations with acceleration. The vertical acceleration is negative 9.8 meters per second squared if up is positive, and the horizontal acceleration is 0, so the horizontal velocity is constant. There's a few different scenarios for 2D projectile motion, but they all work the same way. The horizontal motion and the vertical motion, the x and y motion, are completely independent. The object has separate x and y positions and velocities, which use separate equations. When working with projectile motion, we're usually given the initial height and the initial velocity vector. We need to find the components of the vector, which are the initial x and y velocities. Then we can study the horizontal and vertical motion separately. There's no horizontal acceleration, so the x velocity is constant. It's always the same as the initial x velocity, and the object moves the same horizontal distance every second. The vertical motion is affected by gravity, so the acceleration in the y direction is always 9.8 meters per second squared downwards. In 2D projectile motion, the y motion is the same as 1D projectile motion. The y velocity slows down as the object moves up, the y velocity is 0 at the maximum height, and then the y velocity speeds up as the object falls. The object will be at the same height at equal times before and after the maximum height, and the y velocity is the same at the same height, but the direction is reversed. The actual velocity vector of the object at any time is the sum of the x and y velocity components at that time. At the maximum height, the y velocity is 0, so the velocity vector is just the x velocity. The motion graphs for the x direction are always the same. The x acceleration is 0, the x velocity is constant, and the x position increases linearly. And we can use this equation to find the x position at any time. The motion graphs for the y direction will depend on the initial and final points. But in each case, the acceleration graph is a constant negative 9.8 meters per second squared, if up is positive. The velocity graph is a straight line, and the slope is the acceleration. The velocity curve crosses the horizontal axis when the y velocity is 0 and the object is at the maximum height. And we can use this equation to find the velocity at any time, or the time when the velocity is 0. The y position graph is curved because there's acceleration. The slope at a point on the position graph is the velocity at that time. And we can use this equation to find the y position at any time. The range of the projectile motion is delta x, how far the object travels in the horizontal direction. To find the range, we need the initial x and y velocities. Then, we find the amount of time the object is in the air using one of these equations. Then, we plug that time into the x velocity equation to find the range. If the initial and final heights are the same, like if the object starts and ends at the ground, then we can use this equation to find the range. A launch angle of 45 degrees results in the maximum range, and the range is the same for two angles that are the same amount above and below 45 degrees. And if the object starts at a greater height, the optimal angle is less than 45 degrees. Alright, that's it for this video. Thanks for watching, and I'll see you in the next one.